All right. We talked today in class a little bit about possible reaction orders for this particular series of reactions. First thing we did was we said, all right, what if we add up all the reactions and see what the sum of the reactions would be? We see that there's a D in the products, but then that D is consumed. We see that there's an E in the products, but then that E is consumed. So there's a D on each side, so they effectively cancel out. E on each side, so they effectively cancel out. All right? You'll also notice that B is used in the first step and in the second step, but one of those B's comes back at the end in the third step. So in the reactants and the products, so it's effectively removed. So if this were a one-step reaction, if we sum this all up, what we get is we get A plus B goes to C. A plus B goes to C. So written another way, that would be 2A plus B goes to C. If this were a one-step reaction, the rate law would be dependent on A, and B. I know that's redundant, but it would be dependent on the rate. How fast this reaction would occur would depend on both of the A's and the B. So the way we would write that, since there's 2A, we would go, okay, the rate is some constant. That merely gets us to convert between the units. We would have concentration of A for the one A, concentration of A for the other A, and concentration of B. Written another way, that would be K, cons A, the quantity squared, cons B. So were this a one-step reaction, that would be the rate law. If, on the other hand, let's run quickly. Let's say that the very first step was the slow step. If this were slow, then the reaction would solely be based, or the rate would solely be based on the reactants in that first step. So the rate would be based on 1A, don't forget the K, different K, and 1B. So if this were a one-step reaction where two A's and a B came slamming into each other all at the same time and all hooked together and made this C molecule, which is two A's and a B, then this would be the rate. In this case, what we're saying is we have to have an A slam into a B, and that settles in, makes some intermediary, and then the rest of the reaction goes, but the rest of it goes faster. All right? Another possibility is that same reactions, except this time, this is what's called an equilibrium. It's going back and forth. And then this is the slow step. And then the reaction quickly proceeds at the end to make the final product, excuse me. If this were the case, then the rate would be based on this step. And so the rate law would look like this. Rate equals another K, concentration of that intermediate D, I hope I'm not off screen. All right, and the concentration of B. Now, what we said in class today was that if we were to have this equilibrium, that means in that very first step, the rate forward equals the rate reversed. So the rate forward would be some other constant, concentration A, concentration B. Where do you get that? A, B. The rate reverse would be based solely on some other constant, concentration of D. If we solve that out, we get that K3 over K4, cons A, cons B, equals concentration of D. And now what we're going to do is sub that back in to the rate law, because this step does depend on how much D is there. And that D depends on how much A and B are there. So if we sub that back into this rate, let me use the pink that I used, rate equals K2. Now, we're going to sub in for D. Okay. And so we're going to sub all this in for D. So K3 over K4, concentration A, concentration B. That's all D. And then we've still got a concentration of B in the term. So if that slows, this mechanism is true, fast equilibrium, slow step, then the rate would be K times K over K divided by K times K to K to the squared is still K. Concentration A, concentration B, so concentration B, the quantity squared. So let's review. If it were a one-step process, the rate law would be this. K, A squared, B. If it were if the first step is slow and then the remainder of the steps occur rapidly, the rate would be K, concentration A, concentration B. Different rate. If the first step were fast and it goes into equilibrium and the second step is slow, then the overall rate law would again be different. Concentration A, concentration B, the quantity squared. So if this is the reaction, any of those three possibilities could occur. Now, how do we know which one it is? Well, what we would do, and you'll see this in the next day or two, I'll put that back here in a minute so you can see it. What we were going to do in the next day or two is we go, okay, we're going to have some concentration of A, and then we'll double it. All right? So if my rate law is just some K, don't forget your K, like that, and I have some A, and then I double the A, and the rate doubles, well then it's first order in A. In other words, the two are directly proportional. On the other hand, if my rate